Good morning, everyone, or afternoon, evening, depending on where you are located in the world. My name is Andrew Coger. I'll be presenting today on Altair's side. We'll be first going through the workflows for generating designs for additive manufacturing, and then Niels will be presenting the simulation aspect of simulation for additive manufacturing. So we can jump right into it today. Before we get into the design to part workflows, I'd like to just touch on additive manufacturing as an industry. So in recent years, additive manufacturing has made the jump from capability to capacity. We've seen a number of companies leveraging additive manufacturing, not only for prototype type designs, but also for production level components. And a lot of people hear the word additive manufacturing, they hear it kind of as a buzzword. They don't really understand why it's so useful. So this is because we can generate highly optimized mechanical performance components. We can also create ready to manufacture designs, and of course, time and cost effective production status. So we're reducing the number of prototypes, we're reducing the amount of material waste in the manufacturing processes, and really additive manufacturing has evolved, and it's become clear that these design processes are a very important part of additive manufacturing. So today we'd like to discuss what tools Amphion and Altair can offer to make this process easier. So I'd like to start with a hypothetical situation. Perhaps we have some mountain bike design and we'd like to create a revision 2, and we'd like to design this pivot component you see in the frame here. Now, perhaps this component was designed using a machining process or a casting process previously, but with the capabilities of additive manufacturing, your company has decided that they'd like to make the jump to additive manufacturing. So first, we have to assess the challenges with designing this new component. Here we see a beautiful additive manufacturing design, but have we really considered perhaps the mechanical design? Does this fit into our original assembly? Also, what about the structural performance? We need to make sure that this component is efficient, so either reducing the weight while also keeping the structural performance so this component won't fail during normal load operations. And then finally, if we wanted to update this component for a different manufacturing process, maybe previously, like I said, we were using a casting or machining process, but if we want to use additive manufacturing, we need to make sure that we can actually manufacture this component. So things like minimum member size, things like extrusion direction, those are very important characteristics of a design, and we need to make sure that it's actually possible to create that in manufacturing. So at Altair, we like to use these 3 pillars: performance, efficiency, and manufacturability to help guide our design process. Taking our mountain bike assembly here, we can first assess the performance of this component. So you'll notice in the bottom left there, we have our little pivot design highlighted in blue. Now we need to make sure that this will hold up to our loads. So what we can do is we can build a load case summary using Altair Inspire. Here, maybe we have a number of different mechanical loads applied to the assembly, and we can evaluate the performance of the assembly. After we've done that, we can begin to build the design of the object or the new component using the different manufacturing options. So perhaps we wanted to machine this component. You can see Altair Inspire will create this machined design using the performance and manufacturability criteria. Similarly, we could also do this with an extrusion or a machining process, or indeed, we could use additive manufacturing. Now, I'd like to touch more on this additive manufacturing, as today we are focused on that as a subject. So let's break this down a little bit further. Again, we're evaluating the performance of the component, and we want to address the efficiency or the structural capabilities of an additive manufacture design. Using Altair Inspire, what we can do is we can set different criteria that we need to meet for the component. So here, maybe we're using SLM or binder jet or FDM. Depending on that process, we can see a number of different design options are available to us. Now, for each one of these different processes, obviously there are different things to consider, and this is where these different designs come from. So I'd like to show how this would work in Inspire. So here, what we've done is we've taken the component into Inspire, and we're using our shape control features to help update our design. So in fact, if we wanted to create a split draw mechanism, on this component, you can see we can apply that directly to the component, and we can get some idea for what that component would look like with a split draw constraint on that plane. Similarly, we can do a split draw on a different plane, and you can see how that might look for the component there. Now, if we wanted to do an extrusion, similar process, we're clicking there, choosing our planes, applying that, letting the simulation run, and then we can see our design there. Now, obviously, for an additive manufacturing process, we're not so concerned about split draws or extrusions. We're more interested in print direction and overhang constraints. So here what we can do is we can place an overhang constraint on our component with a print direction based on the plane. And of course, when we run through the simulation, create our optimized design, we can see how that might affect the component. Now here we can change our print direction, and you'll see the component looks slightly different based on that print direction. So using these tools, we can develop our design with the consideration for things such as overhang, print direction. If we were doing a stamping or manufacturing or casting process, these designs are all guided based on manufacturing principles. So here, as a summary slide for this component, you can see perhaps if we use conventional casting, our component looks like this. But in fact, if we were to use an additive manufacturing process such as powder bed laser melting, binder jet, or fused metal deposition, the component has slightly different configurations because we've applied those manufacturing constraints in simulation. Instead of updating our component manually, going through multiple revisions, we're doing this all through simulation-driven design philosophy. Now, let's come back to our mountain bike model here. If we wanted to update this pivot suspension component, and right now it's being produced using a machine process, and perhaps we know our loads or boundary conditions, our objective here is to create a new novel design while maintaining performance without the weight penalty. Now, the first step using Inspire is to generate a motion model. Now, this helps us assess the resultant loads applied to the component and allows us to redesign using these loads. So you'll notice here, we've created this placement force on the rear axle. We have this mechanism causing our pivot suspension arm to react. Now, of course, with this motion model, we can also extract internal forces on our component. So here you see a contour of those stresses through the component. And this helps us build a full picture for what our component is subjected to and how we need to update the component's design for additive manufacturing. So when we want to begin the optimization process, we take that component and we generate a design volume. Now, these design volumes are supposed to be the maximum volume possible for optimization volume. This allows the software to control the removal of material and only place it where it's necessary. You'll also notice we have some non-design regions adjacent to our design volume that are preserved. This is to help with the transfer of loads through the component and helps build a clear picture of what the component is subjected to. At this stage, we can also do our manufacturing constraints with symmetry, and you'll notice here we've also done our print direction constraint. This helps inform the solver or the optimization which direction or where we can place material, and also any symmetry within the component. Now, after we've built this full picture for our components' use cases, we can also begin to build different designs depending on the manufacturing process. So here you can see we've evaluated not just a design for 3D printing, but also for split draw direction, extrusion, and a fourth split draw direction. And depending on each one of these different optimization volumes, you can see our mass for the pivot component is affected accordingly. At this time, we can also check the performance of each one of these with compliance. So you'll notice with our print direction design space set, our compliance falls right in between what a split and an extrusion manufacturing constraint would suggest our optimal design is. Now, after we've evaluated the different manufacturing constraints, we've generated an optimized design, the next step is to actually create a concept. So with this information on the optimization and the necessary material to be placed, we generate this concept using polyNURBS. So here you can see kind of a final concept design based on the optimization that we've run. Now, I will now hand it over to Niels, who will describe some of the simulation tools we have available for printing. And he can show you how we might use this concept in the print simulation. So Niels, I'll hand it over to you now.
All right. So yeah, we have just seen how to create a nice part design for some certain application. And I want to follow up this with the manufacturing and printability, and especially additive metal additive manufacturing. So Additive Works is specialized on metal additive manufacturing, and we are focusing on simulation-based job preparation. So before I start to show the workflow for the part, I'd like to speak a little bit about the challenges in metal AM. We all know about this process, and they are really nice and complex filigree parts and components generated. But in fact, there are also a lot of issues you may not see that often in media. But basically, it's a welding process, what means that we have all the effects we know from welding. Hot material is cooling down, contracting, and so distorting the material, leading to cracks, and also other issues like overheating can appear during the process. So it's important to have a design that can easily be manufactured, and we have just seen how to create a design based on a load case. But the issue of finding the build direction is basically always there. So what we can do as a first step with one of our Amphion modules is to give a feedback for a design and what would be the best orientation. And using this feedback, you can then consider some direction during the optimization in Inspire. And this is the first thing I want to show here. So as the examination module is probably not that known or famous as we are usually showing simulation, I have a small introduction of this module. So basically, we are using an import like an STL and rotating this over all possible orientations, analyzing build time, support volume, the post-processing effort, but also distortion. And based on this, we can create two-dimensional maps for the orientations. So both axes are one angle for the orientation, and high values are bad values, green values are the good values. What the ideal orientation is depending, of course, on the application. For example, you need to build your parts very cheap and fast, then build time is maybe more important than deformation. So in the software, there are sliders, and you can interactively find out what's the ideal build direction for your needs. Like for support volume, you get the green point here, and it's for this example bracket laying down in the chamber. But if you orientate it against deformation, you get like the upstanding result here, because here we have less cross section and strain accumulation will not be that bad. And for post-processing, for example, you would get something like this based on the numerics. So here we have less surfaces to be finished after the process. So for the design we have already seen, we also did this, and we applied some application-specific constraints, what was in this case to reduce the deformation or to not have high deformation. So the maps for this part, for this design, looks like that. So for this initial orientation where it's laying down, the build time is good because it's not that many layers. Support volume is also good. But post-processing might be an issue because you have a lot of faces to support here. And also deformation is bad as the cross sections in the XY plane are big. So now we can use the slider and exclude here the red regions of deformation in order to get the best orientation without high deformation. And if we do that, the point of the ideal orientation is moving to this point here. What is the gray overlay here? So this is the new orientation. This is the ideal orientation under the constraint of having less deformation. And based on this new orientation, there was like the other loop for the design optimization done in Inspire, and we got this new design. You already saw it in the slides before, where this orientation was applied during the topology optimization. And if we would now orientate this, and I will show it with the next slides, we will get like the ideal orientation as it is, because this is already then the ideal orientation. And you can see, for example, that here we would have something more to support if it's upstanding, like these connection arms here. And with this design, we don't have it. We all see these 45 degrees angles everywhere, and we don't need a lot of supports, for example, for this part. So with this feedback loop, so in this time it was done once, and we got a very good result. But of course, you can do it multiple times. And basically, I think it should convert really, really fast, because if you already consider build-up direction during the optimization, it's very likely that the ideal orientation will be the considered one. So second step is the job preparation itself, so preparing it for manufacturing, and there can be done a lot of mistakes. And currently, it's based on know-how and experience, but we are doing this simulation-based. So of course, with this first examination module, we determine the build direction. Then we create supports, but we optimize these supports in order to avoid cracking and delamination from the base plate. We run a mechanical analysis to predict the printability, and we compensate the deformation using pre-deformation module afterwards to have a really near net shape part. Once the build job is finally set up, we run a thermal simulation to prove for thermal stability, and we can do a thermal adaptation. And then it can be sliced, hatched, and sent to the machine. So as mentioned, the first step is the orientation, and here we get other maps for the new design now, and already the best orientation is good for deformation, is good for post-processing, is good for or has less supports, is a little bit higher in build time, but it's okay. And so we have a really good result without adding some certain user criteria. And we can really compare and understand the differences of the design if we have a look at these maps. You can see how the map for support volume and also post-processing and of course deformation change just by the new design. So this is very important and is something like a feedback of your design, and but of course also for the orientation you should print it. So in the end, the result was that there's no changes needed in the orientation, as we just got it from Inspire in this direction. So the second thing, the third thing now is to create the support structure, and here we have let's say a very cutting edge module, because we don't start with the actual support structure and are then strengthening it, but we basically use a similar approach like topology optimization to create the support. So we start with the geometry and a certain orientation. We are adding a design space for the supports, like for topology optimization. For example, based on an overhanging angle criterion, or you load it from other software. And then we are not creating supports, but running a process simulation where failure strain is used in order to increase the density within the support material. And based on this result, we create the actual support structure, also considering a certain stress in interfaces. So you can target a stress in interfaces, and the interface width will be generated accordingly. So in the end, you get a wall structure with perforations depending on the local density. And if a closed wall is not strong enough, we are adding more and more walls. So with this kind of structure, we can realize, I would say 5 50% up to nearly 100% of volume densities. So we can make sure that parts will not crack from the base plate or from the supports, or the supports from the base plate. For the part we are discussing, I like to show the results here. So in the first loop, we have like an average density everywhere, but already in the second iteration, we see that there's only a strengthened structure here close to the base plate. And after 5 more iterations, the final result looks like this. So it's converged, and we just have a little bit more strengthened structure here, and probably a little bit more reduction of material. So there was a focus on reducing material within the supports, not preventing deformation, because we have pre-deformation, and also we oriented it against deformation. So we won't optimize also supports for deformation. So deformation was a little bit increased over the iteration of this optimization, but you can see the material usage was decreased by nearly the half compared to the regular support structure, like in the first step. So we save a lot of material of the supports here, and of course a lot of process time, what is even more expensive. The generated supports look like that. So as mentioned, 2D block support structures, but now we can check that there's a difference and a grading, for example, of the perforation, like here. So if you see the small image above, there's some higher density here close to the base plate, and we can see that perforation is more and more closing. We can also see on the top view that there are doubled walls, like a double thick wall in the corners to strengthen the structure and avoid delamination. On the right-hand side, where you see the green dots, we can see that the density is at minimum, meaning we have maximum perforation, I think 70% here. Of course, this is depending on the recoater and the machine, but this is saving, of course, a lot of process time. And we can also see that interfaces size is changing with the geometry. So we have more loads on the right and on the left compared to the middle. And we can see this in the interfaces because they're generated in a way to have the same stress state, so they have a difference with. The next step is the process simulation. What is a feature added by the beginning of this year? And here we have 3 possibilities for checking if a print will be succeeding. The first is the recoater crash. So if the recoater is somewhere hitting the part, and the process usually aborts them. The other is cracking, if the part cracks from the supports or supports from the base plate. A crash may follow because the part can then freely move up. So we predict this by using a plastic strain criterion, and also high deformation can be tracked. So in the software, you see like some graphs for that, and you can see once this one of these will hit 100%, the print job will probably fail. In this case, all is good. Deformation is not that interesting because we're using pre-deformation afterwards. Plastic strain is okay, and we created supports with using optimization. So the critical criterion for plastic strain is already in there, and recoater crashes are in this case not likely. So the result you have seen, this is the deformation after the process. So after the build-up, where also printability is checked. But if we don't do a heat treatment, for example, of titanium here, we also see some spring back and stress relaxing effects if we cut the part from the base plate. So we can calculate that, and also calculate the support removal, what has some effect. In the end, we have a maximum deformation of 800 microns here, and we can use this result and virtually pre-bend the part against this deformation. So if you print this and you get this deformation, you end up with the part in the right shape. So in principle, we would now manufacture the parts, we would set up our build, but let's talk a little bit about thermal simulation. So thermal simulation became very important because we have, meanwhile, bigger machines, kilowatt lasers. You may have heard about a machine with 12 lasers, but also 2 and 4 are more and more common. So there's a lot of energy input to the process, and parts will overheat in some cases, leading to bad results. And for that, we do a global build rate analysis. So we really calculate the build rates, and then on the second level, do the thermal simulation per part. And there are a lot of issues of thermal instability, like we have unwanted phase generation. You can see it in this color difference, for example. Material properties will vary. For example, if temperature is increasing with the height, we have different cool rates, and we generate different grains. Also, process distortion is becoming unpredictable and very complex, and also inducing high additional deformation. So deformation of centimeters usually only occur if an overheating was there. And we also see, of course, shrinkage, because if the part was hot after the process, it's cooling down and will just shrink. So if we now analyze a build job of printing 9 of these parts with the support structure and with our preparation, the process will take 1 day and 2 hours. But maybe one day we only want to print 4 of them. So in this case, the process only takes 14 hours and 40 minutes. And now the question is, do I have the same thermal conditions? Do I get the same result from these 2 build jobs? And we can simulate, based on these different build rates here, what's the maximum temperature. For the left-hand side, it's 300 degrees. So I would say it's okay for titanium. On the right-hand side, we see nearly 400 degrees. So I would say, oh, there's some hot spot here, and we can expect additional bending, like in this thin connections and so on. So we're definitely manufacturing the part in a different quality on the right-hand side. And this is the issue we want to solve next. And here we have the new module for thermal adaptation, just released a few weeks ago officially. And here the goal is not only the prediction of overheating, like just discussed, but preventing these unacceptable overheatings. And of course, you have to choose what is unacceptable. But the conventional usage before, also including simulation, was more like you have a print job preparation, you run the thermal simulation, and then you loop back. And then you can change the design, you can change the nesting, like adding more parts or other parts. You can change orientation to have better heat conduction, and you can change the supports. And you could also change the minimum layer time. So you could add a waiting time to avoid other changes. And then the machine is basically just waiting for cool down, but you can achieve thermal stability. So we can check this with the simulation. And once it's good, we go to manufacturing. The new workflow will be the simulation-based job preparation workflow. Like we do the print job preparation, we run a thermal adaptation, and as an output, we get waiting times per layer. So in each layer, there should be a certain waiting time to not come over the temperature. And this is what the thermal adaptation module is doing. And then you go directly to manufacturing. So there's no loop anymore. What's the method here? Basically, the user is defining a maximum temperature. So this is all you need to do. What does the simulation? It is a simulation, of course, of all parts, because if one part's getting hotter, you want to cool this down. And optimizing these layer times. So based on the temperatures we're calculating in the software, we're calculating the right time to wait in order to get to the maximum temperature the user has entered. And based on that, we get a stack of waiting times, waiting time per layer, and we generate those parts from there. Because those parts can be loaded to the machine, and it's the most easy way today to realize different waiting times over the height of the layers. So for example, for such an overheating part, a ghost part would look like that, and the bigger the cross section is, the more waiting time is. So this second part is not really exposed, it's not really built, the powder is not molten, but it's having same process parameters, but for example 0 or 1 watt. So you add this to the print job, you use the same scanning speed, because via this cross section we are realizing this waiting time, and you assign 0 watt, or for EOS it's 1 watt as layer power, to not really melt this, but just enable it as a waiting time. And of course, this is a workaround, but with that, you can realize it on, I think, all machines. And in future, we're looking forward to have better interfaces to pass these times to machines and not create STLs out of it. Okay, so applying this to our part, and we could say we aim at a maximum temperature of 300 degrees, and we already know about that. We also know about this job, what was basically the fail, and we discussed the minimum layer time. And in this case, 40 seconds would give us a good result. So with a layer time, constant layer time of 40 seconds, we will get this in 22.5 hours, but below 200 degrees. So this is the, I would say, the state of the art, how to manufacture this with same conditions like in the 9 parts build job setup. But with the new ghost part, we can add this part instead of using minimum waiting times, and we can achieve a maximum temperature of 300 degrees. So this is how the part looks like, and the build time is only 16 hours here. So basically, from the same maximum temperature, we were able to decrease by 28% from 22.5 to 16 hours. So there's some benefit in time, and it's obviously why we have this benefit. If you see this ghost part, there are no waiting times in the first half of the process, because there it's not overheating. It's only overheating in the second half of the part, in the upper region. So waiting times are added only there where it's needed, and you can see it's also changing with the layers, and not that easy, but of course you can just like add it to the machine and print it. So the result is a first time right printable and nested build job here, and basically we have two possibilities discussed, like we can print these 9 because we proved that it's okay from thermal conditions, but if we want to print less, like 4, we know how to derive the ghost part and then manufacture it on the same conditions. All right, so let me conclude my presentation. So we started with an optimized design, optimized for its application. We did a feedback loop with the examiner module for the print direction. And then we got, or from Inspire, the optimized design, not only for application, but also optimized for 3D printing, or for SLM in this case. So then we ran the simulation-based support optimization, created supports. We checked for the printability, compensated deformation. We have proven the thermal stability, and also generated a ghost part in order to have a thermally stable job. And in the end, I think this is kind of a reduction of number of experiments by more than factor 10, because usually you do printing for that. So you have a design, okay, let's print it to check if it's printable, and so on. So you change the design. So if you have 2 loops for design change, 2 loops for creating better support and printing it again, 2 loops for checking printability with the support, 2 loops for doing something against deformation if you don't use simulation, and also 2 loops to check for thermal stability, or think about minimum layer times and so on. You lose like 10 experiments just to determine the final build job, and this is all the time, and of course all the cost for the machine we want to save here.